Hello again. We will continue this course by discussing an experiment that will not only validate Einstein's photoelectric equation, but will also allow us to determine a value for Planck's constant, h. But first, we have to understand the concept of a stopping potential. This concept is similar to having a ball moving up a smooth inclined plane. Imagine that we vary the height h such that the ball just reaches the top at Q. At this instant, we can say that all the ball's kinetic energy has been converted to gravitational potential energy. So we can easily determine the velocity of the ball by instead measuring the height h, since we know that half mv squared would be equal to mgh. Now, this experiment will not involve inclined planes, but rather a photocell, which consists of an evacuated glass bulb with two connections, A and C, one of which is a metal surface, which is here shown in orange. When this metal is exposed to suitable electromagnetic radiation of the right frequency, photoelectric emission will take place, which means that electrons will be emitted from the metal surface. The ejected electrons will reach terminal A and cause a current in the circuit unless we connect the power supply such that A is negative and C is positive. In other words, we apply a reverse voltage across the photocell. Why? Because by connecting the power supply as shown, the ejected electrons will be repelled from reaching A. Don't forget that electrons are negatively charged, and so if terminal A is connected to the negative terminal of the battery, then the electrons will experience a retarding force, an electric repulsive force. Now this depends on how large the applied voltage is. If V is too low, then the electrons will simply be slowed down, but they would still make it to A and the current would still be detected. This is like saying that we have a low height h for the inclined plane. The ball would be slowed down, yes, but it would still make it over the top. On the other hand, we could increase the reverse voltage across the photocell sufficiently such that even the most energetic electron will not be able to reach terminal A. And how can we know that no electron is reaching A? Of course, electrons are invisible to the naked eye. However, we can detect them by simply connecting an ammeter in the circuit, which measures the flow of current, in other words, the flow of electrons. Thus, when the ammeter reads 0 amps, then we are pretty sure that no electron is reaching terminal A. The stopping voltage, usually denoted Vs, is that particular voltage at which the current just becomes zero. Meaning, this is the voltage which just stops electrons with maximum energy from reaching A, and is not surprisingly called the stopping voltage or the stopping potential. Now, the work done in moving a charge Q across a voltage V is QV. But Q is now the electron charge E, the constant 1.6 times 10 to the minus 19 coulombs, whereas V, as we said, would be the stopping voltage Vs. Hence we get W is equal to VE Vs. Thus, the loss in kinetic energy of the electron, half mv squared, is equal to E Vs. If we consider again Einstein's photoelectric equation, HF is equal to W plus half mv squared. Please bear with me because there seems to be a slight confusion in the symbols used, because this W here stands for work done, whereas in Einstein's equation, W is denoting the work function of the metal surface. So these W's have nothing to do with each other, okay? So as we said, we can substitute EVS instead of half mv squared, and by rearranging such that Vs is subject of the formula, we get this equation here highlighted in yellow. This equation shows that if we had to perform the experiment for various frequencies of light, and for each frequency we measure the stopping voltage Vs, then a graph of Vs against F, which means stopping voltage on the y-axis against frequency on the x-axis, this should be linear with a gradient equal to h on E and a y-intercept which is equal to minus W on E. Here the symbols H mean Planck's constant, E is the electron charge, whereas W is the work function of the metal surface. It is also interesting that the x-intercept here, which is the point on the x-axis at which Vs is 0, denotes the threshold frequency. So we start getting photoelectric emission from F equals F0, the threshold frequency above. The results we just mentioned are summarized here. So thus, we can determine Planck's constant h from the gradient, whereas the work function can be determined from the y-intercept. Now, this figure, okay, so we go a little back. This figure illustrates, so I'm referring to this circuit here, the basic setup required for performing such an experiment. We would require, as we said, a photocell labeled X, a potential divider which would allow us to vary the voltage across the photocell. Of course, we would need an ammeter to monitor the current in the circuit. In other words, to check whether electrons that are emitted from the metal surface would be reaching terminal A or not, and also a set of color filters to vary the wavelength of light reaching the metal surface. Now here we have a graph of current against voltage, which shows that for various wavelengths of light, which means that for various colors of light, we get different stopping voltages. The highest stopping voltage, which is here denoted V1, is obtained for the shortest wavelength of light, corresponding to the highest frequency. Remember that energy and frequency are directly proportional to each other. It is interesting to note that if a positive voltage is applied across the photocell, then we get the same current irrespective of the wavelength of light. Of course, assuming that the intensity of light is kept constant. Now, notice what's happening here. For the same frequency of light, meaning that if we keep on using the same color, if we vary the intensity of light, we get different colors, we get different currents if we apply a positive voltage. However, when we apply a negative voltage, the stopping potential is the same, since, as we said, the energy of the ejected electrons is independent of the light intensity. The second graph shows that the current is directly proportional to the light intensity for light of the same frequency or color. Lastly, this graph of stopping potential against frequency for different metals shows first that we get the same gradient, which means that the lines are parallel to each other, and this is as expected since we just saw that the gradient is equal to H on E, both of which are constants, and thus the gradient is constant. It is independent of the metal used. However, we get different x-intercepts since each metal has its own threshold frequency. In the next session, I will show you a simulation demo of this experiment.